Hello, and welcome to the post-lab reflection for the Module 7 lab, molar volume of gases. In this experiment, we're going to be making an at-home version of a eudiometer in order to capture the gas produced in a few reactions. By observing the water displaced by the gas that we capture in the reactions, we will be able to verify the molar gas volume of carbon dioxide. So in this experiment, we're going to be looking at the moles of carbon dioxide produced by the known reaction between sodium bicarbonate and sodium carbonate with acetic acid. What we'll be doing is causing the reaction to take place, and then that reaction will create a displacement of water, and we will use the displacement of water to calculate how much carbon dioxide gas was produced. Using that, as well as the amount of sodium bicarbonate and sodium carbonate that we're going to be using, we'll be able to take all of that information together with the temperatures and then the pressure in the air, and we will be able to determine the moles of carbon dioxide that are produced in this reaction. In terms of safety preparations for this lab, of course, I will be wearing the splash goggles since the chemicals that we're going to be using are very irritating to the eyes. Other concerns that we have involve broken glass, since we do have these glass rigid tubings. For this, we are going to be using the petroleum jelly to make sure that the rigid tubing is very well lubricated when they're being inserted into the stoppers. Another precaution will be when inserting the tubing into the stoppers, using a twisting motion so that we're relying on torque instead of pushing the rigid tubing in, which could cause it to break. Another concern in this lab will involve pressurized containers. That's why we have the rubber stoppers that we're going to be using that will allow the pressure to not create any sort of hazard for us. We're also using plastic Erlenmeyer flasks, so we shouldn't have a glass concern as far as the pressurized reaction goes. Here we have everything set up for the first trial, and the first trial will involve the sodium bicarbonate. We have 25 milliliters of vinegar here, 200 milliliters of distilled water, and once the reaction begins to occur, the water will displace into the graduated cylinder and the measurements will be taken. At the end of trial 1, I have 69 milliliters of water displaced. Now I'll be performing the second trial with the sodium bicarbonate. Here are the results for the second trial for sodium bicarbonate, and the water was displaced at approximately 99 milliliters. Now I'm going to be doing the first trial with the sodium carbonate. So the results of the first trial for sodium carbonate are interesting because I didn't actually get any water in the graduated cylinder. I did see the reaction take place and the water began to go up through the rigid tubing, but then it reversed course and went back in. So hopefully I will get better results with the second trial. And now I will perform the second trial using the reaction of acetic acid with sodium carbonate. Trial 2 for sodium carbonate produced way different results. Whereas the first time I couldn't get any water to displace, now I have more than what we can measure in the graduated cylinder. So what I'm going to do is pour out the excess into this clean glass beaker, measure the 100 milliliters, and then pour that out and then measure the excess to find out how many milliliters was displaced. So we have 27 milliliters of excess, which means that in total there were 127 milliliters of water displaced. Here's the table showing the results for my calculated molar gas volumes in each experiment, or in each trial I should say. Notwithstanding the first trial with sodium carbonate, where I got no results, you can see that the percent error is pretty significant for each trial. And this could potentially be due to several sources of error within the experiment itself. I wanted to test if the scale is the potential source of error, so I took out my food scale in the kitchen and tarred the weigh boat on it, and then measured out approximately 10 grams of just plain white granulated sugar. See, we read 10 grams on this scale, and then I tarred the weigh boat on this scale as well to see what the measurement would be. And it's 7.1, so that's about a 3-gram difference between this scale and my food scale. It's also possible that there was a leak in the tubing setup or a leak from the stopper that caused the error. It could even be a combination of these two factors, the error in the scale reading and a little bit of potential leakage that contributed to the high percentage of error in the results of the experiment. I think the best thing that could be done in this situation is try to reattempt the experiment, eliminating as much as possible the possibility of any potential error that has been identified, and seeing if perhaps we can get the results closer to the theoretical values. And just to briefly touch on the role that water vapor pressure played in the experiment, and especially in the subsequent calculations, we know that we needed the pressure of CO2 in order to solve for the volume in our rearranged combined gas law equation. But in order to find the pressure of CO2, we needed to subtract the water vapor pressure from the atmospheric pressure in order to get that result, and that's the role that it played. The critical thinking prompt for this week's post-lab reflection deals with what effect the limiting reactant mass has on the molar gas volume in a gas-producing reaction. Well, we know that in a gas-producing reaction, the limiting reactant is the substance that is completely consumed, which then determines the maximum amount of product that can be formed. The molar gas volume refers to the volume occupied by 1 mole of gas at a specific temperature and pressure. The limiting reactant mass directly affects the amount of product formed and consequently the molar gas volume. This is because of the ideal gas law, which is represented by the equation PV equals nRT, and it shows that the volume of gas is directly proportional to the number of moles, which is the N in that equation, of that gas. Therefore, if the limiting reactant mass determines the number of moles of gas produced, it will also determine the molar gas volume. Moving into the self-reflection portion of the post-lab video, I'm going to be talking about how the activities in this module connect to what I've learned in the lecture, and a little bit about how it connects to things in maybe my professional or personal life. For the connections to lecture concepts, of course, we have the combined gas law and the ideal gas law, etc., where we can see the relationships between pressure, volume, moles, temperature. And then we can see this very clearly in the reaction, because when we have all of these elements combined, the volumes and the pressures, it helps us to determine the molar gas volume, because we can use those relationships to our advantage when we're taking a reaction and then observing the results. So that's a really interesting part, that a really interesting connection that this makes to the learning. As far as connections to my professional or personal life, I have an acute interest in weather and meteorology, etc. So looking at the role that atmospheric pressure played in this experiment was really cool to me. And I've seen this in action in my personal life before, such as when the pressure changes whenever it starts to rain. I've seen carbonated drinks overflow and start to really produce gas whenever that pressure change happens. And it's really cool to see that in this experiment, because we needed to know what the atmospheric pressure was in order, and the water vapor pressure, in order to figure out what the pressure of carbon dioxide is. And to me, that was just a really interesting aspect that is closely related to a personal interest I have. And that concludes the post-lab reflection for the Module 7 Lab Molar Volume of Gases. Thank you so much for your time. Please let me know if you have any questions. Thank you.